Okay, I started to record it. Right. So yeah. So let's say there is some random variable which we want to model, and typically what we do now is that we assume that there is some distribution associated with this random variable, and if this distribution has some parametric form, we can use some maximum likelihood estimate or something to estimate those parameters. Right. So that is what we have done so far. Um, what are the difficulties which you might face in this scenario? Can somebody try to say what are the difficulties which one might face, or uh, will this work always? I'm asking you a question. Will this work always? What are the difficulties which you might face? How many of you are on campus? Please raise your hands. Only two people are on campus. Okay. 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 Fine. Yeah, you can lower. Yeah. So do you have an answer? Did you understand the question? What I asked? Abhishek?
Yes, sir.
Did you understand what I asked?
Sir, actually, one class just got over, so I'm just reaching my place. I didn't listen to the question.
Okay. Okay. Yeah, you can mute yourself now. Let me ask somebody else. Jay Sharma. Did you understand what I asked? Lokesh, are you there? Ashutosh?
So, like, if the distribution is not normal, or well, like it's not Gaussian distribution, uh,
Uh-huh.
then the like we assume that maximum so the likelihood function that probability we assume it to be normal Gaussian distribution.
Hmm.
But if it's not Gaussian, then I think the likelihood may not be maximum for sample mean and sample variance.
No, no, maximum likelihood will always compute it will give you the parameters which maximize the likelihood. That is how it is done. So it is always, likelihood will always be maximum.
So like we assume, like when we code, we already assume that it's Gaussian and we do not compute the maximum likelihood when we code, not when we
Hmm.
write. So we firstly take like the sample mean and sample variance
Hmm.
and assume it to be the that likelihood will be maximized for
Hmm.
this value of mean and mu and sigma square.
Hmm.
So we take it while calculating the that probability. So that may be an issue.
No, I'm not understanding what you're saying. Anybody else wants to say something? So the
So
question I
please
asked was,
clarify. Yes.
yes, yes. First, repeat the question. What I asked somebody. Yes, Vikas, you want to answer?
So please clarify your question first.
The question was, we have some data and we are going to get some maximum likelihood estimate of some parameters of the distribution which is we assume is going to describe the data. What is the problem which we might face? Is this
So
procedure always guaranteed to give you correct answer?
actually the basic assumption which we follow in naive ways, na, that's all features are independent each other.
No, no,
And
no, nothing to do with classification. I'm not talking about classification. I'm just talking about modeling the random variable. See, the problem is in the assumption. How do you on what basis are you going to assume that it is Gaussian? How do you know that it is actually Gaussian? No, till now we have not addressed that issue. I mean, because some random variable could have any form. It need not be any of the standard forms which we know. It could be any form. It could be some arbitrary function as long as it satisfies the properties of a density function. A particular random variable can have any form, and it's going to be even more complex if it is multivariate, like if it has multiple dimensions, if it has multiple vectors. Simple example, for example, let me take this. Let's say, for example, there is a data D which represents number of people traveling in a particular bus route. Okay, so let's say we have observations for every half an hour, let's say. Let's say we have done it for 100 working days. Okay, so that means let's start. Let's say we start at 6 a.m. in the morning. At 6 a.m. you measure how many people have between 6 and 6:30. You accumulate how many people have traveled in that bus route. So there may be multiple buses, and you between 6 and 6:30 you find a count. Okay, some x1 people have x1 people have traveled between 6 and 6:30. Then from 6:30 to 7, x2 people have traveled. Like that you do till let's say 6 p.m. Okay, this is some xk. Then you repeat this, let's say on Monday, Tuesday, Wednesday, like that you do up to 100 working days. And you have xn. Total, this is the number of observations which you have. Each xi tells you the number of people traveling traveling on that route for some particular half an hour. This xi corresponds to one of those half an hours. Right? How will this distribution look like? How will this so if you have this data, and if you are going to assume it is a Gaussian distribution, is the data correct? Suppose it is a Gaussian distribution. Maybe I think I should just okay. So let me draw the distribution. So suppose it is suppose we assume it is a Gaussian distribution. Okay, and this Gaussian distribution, if I so I think I should probably refine how I've done this measurement, but let me tell you what I want. So this is let's say the time, and if I fit a Gaussian distribution, no, not time, this should be the if I fit a Gaussian distribution to it, I might get something like this. Some distribution I'll get. Some PDF I will get with some mean and variance. Okay. It's not very clear. Okay, some PDF, some Gaussian distribution you will get. But for example, the actual distribution may be like this. There may be, let's say at certain times of the day, there may be a peak. Let's say during morning rush hour, there may be a peak. And let's say in the evenings when people come back from office, there may be another peak. And maybe in the afternoons, it may be a little less. So actual distribution will be like this. will not be really a Gaussian. It is actually a distribution like this. The actual distribution is actually, it has got two peaks. And if you model this as a Gaussian, you will get something like this, which is clearly not the same as this. Did you understand what I'm trying to say? So a distribution can have any shape as long as it satisfies the properties of a PDF. So in this scenario, it is not correct to model it as a Gaussian. The biggest problem with which a Gaussian distribution has is that Gaussian is easy to use and all that, but Gaussian distribution problems is it has got it is unimodal. Unimodal means it has only one peak. So many distributions have this limitation. So to model arbitrary shaped distributions like this, we should use what are called mixture distributions. So mixture distribution is nothing but a linear combination of distributions which can describe any arbitrary shaped density function. So for example, this particular thing which I showed, it can be made up of, let's say, this particular case itself. You can have 3 Gaussian PDFs, which a combination of which is describing this underlying complex PDF. So we can use what is not, rather than one Gaussian, we can use a mixture of Gaussians. So this can be modeled as a so need not be Gaussian, it could be mixture of anything. Okay, so you could have mixture of Bernoulli or mixture of Wishart or whatever you want. So in the multivariate case, I will write that as K equals 1 to capital K pi K. Each pi K is normally distributed with a mean mu K and a covariance metric sigma K. So what we have done is we have now taken not one Gaussian, but we have taken multiple Gaussians and we are giving each of them a weight. And that is going to describe this entire random variable. Did you understand what I'm saying? So this, for example, you could have, let's say, you could give a weight here, let's say, 0.4, 0.4, and 0.2. So the linear combination of these Gaussians describe this underlying random variable, which has a complicated underlying PDF. And this kind of mixture distribution or a mixture of Gaussians in this particular case can be used to describe any arbitrary shaped PDF. So this forms this is what is known as a mixture distribution, or this is also called as a mixture of Gaussian, or sometimes it's called a Gaussian mixture model. Also called GMM. Okay. Ooh, I started on the last page. Okay. Let me go back to this. Is there a way to Okay, I'll do it in the end when I upload the slides. Okay, so that is the Gaussian mixture model. So let me write that again here. K equal to 1 to K P of X by K normal distribution X given mu K sigma K. So okay, so now given this, what can you say about this? What can you say about this mixture model, this Gaussian, in this case, this particular Gaussian mixture model? What are the now, based on what you have studied so far about maximum likelihood estimation, how can you extend your maximum likelihood estimation for this? What so from here, what is known and what is unknown? What is by what is written on the screen? Can you tell me what is known and what is unknown? Because what is known and what is unknown? Anybody?
Sir, the weights and values of X are known and mu and sigma are unknown.
Mu and sigma, but how many? See, X is the only thing which is known. X is given from here, the data. This data is what is forming X. This data, this is your X. This is given to you. Okay. This is given to you. So X is definitely known. What is unknown? So Abhishek, why do you say that weights are known?
Sir,
Who told you? Who told you how much weight you have to give? Pi k is unknown. Mu k and sigma k for all k is unknown. Pi k is unknown for all k. And what else is unknown? What else is unknown? K is also unknown. You don't know how many mixtures you must use. Do you want to use 2 mixtures? Do you want to use 5 mixtures? That we will not know. So we can try and use maximum likelihood estimation to determine these values, except for k. K is a hyperparameter. In the maximum likelihood case, k is a hyperparameter. You need some heuristic way to know what is k. So in general, suppose you are given some data, univariate data, let's say, univariate data, suppose you are given some univariate data, how will you determine in general which distribution it might be following? How can you know? Or how can you guess what distribution it looks like? Some univariate data is given. I repeat, some univariate data is given. You are trying to fit a distribution to it. You don't know what form it is. But you want to at least make a reasonably good guess whether it is a Gaussian or whether you should use a Gaussian mixture or whether you should use a student's tree distribution or whether you should use exponential, whatever. So how will you make that good guess? Anybody? How will you do it? One way to do it is by plotting the histogram. Plot the histogram. This will give you a reasonable idea what distribution it follows. Okay, plot the histogram. The histogram will help you. So especially if it has multiple peaks, multiple modes, then you know that you are better off using a mixture model. And the number of peaks in the histogram will also give you a rough idea of what should be k. Okay, so now if k is known, if you somehow find out what is k, what is the k to use, what are the problems which you have to face now? You have to estimate still the various weights for each mixture, for each of the components. You have to identify what is the pi k, and for each of them you need to have its own mu k and sigma k. Okay, so as homework you can work out how many parameters you need for this Gaussian mixture. This particular case, I will call this equation 1. Determine the number of parameters to estimate in equation 1 given k, let's say. Okay, I leave that to you. Okay, so now we will come back to Gaussian mixtures later. We will not cover it right now. So you can imagine that the simple maximum likelihood what we covered for the univariate Gaussian will not directly work here. For the unimodal Gaussian will not work here. Okay, because it is more complex than the simple sample mean and sample variance is not going to help you. So there are more sophisticated techniques to estimate the maximum likelihood estimates of all these parameters. And just to make this complete, this will also require that, because to satisfy the density function requirements, you should also have that the sum of pi k goes from 1 to k is 1, and pi k greater than no, I think I'll just write it as 0 less than or equal to pi k less than or equal to 1. These are the two constraints which we have to put on pi k, so that this p of x in this form, this mixture distribution, is a valid probability density function. Basically, it's this kind of combination, which is basically that the sum of the weights add up to 1. It's basically called as a convex combination. This is essentially a Gaussian mixture model is a convex combination of Gaussian distributions. Okay, so before we will cover this a bit later, but before you do this, again, an idea coming back to this would be, so if you see the data for this kind of a thing, you can see that, let's say, I mean, so you can see that there is a distinct clusters of data can be seen here. So for example, if it is in a 2D case, for example, let's say we have a two-dimensional data. And suppose we have some data like this, some set of data like this. This is of the same class, okay, data belonging to the same class, or this is some data. So if the data forms, this is two dimensions of the data. So in this case, if you fit a two-dimensional mixture model to this, see if you fit this as a single 1D Gaussian, your Gaussian will look like this. This is, let's say, the same data. If I use a one-dimensional Gaussian, that Gaussian is going to look like this. But on the other hand, if you use a mixture model, this is, let's say, the same data. If you use a mixture model, the mixture model will look like this. There is the first mixture will be here, will model this, the second mixture will model this. This is, let's say, the data using a single Gaussian, using a mixture model. K equal to 2. So essentially, when you have this kind of multimodal data, this is related to the concept of clustering, because essentially it can be seen, or it can be shown that the two components of that mixture model, or the various components of the mixture model, naturally form clusters. It naturally forms clusters. So this leads us to first do a treatment of clustering, and then we will come to the mixture model, because in many cases clustering is used as an initialization for building the mixture model. That is why we need to first cover clustering. And clustering will depend on the how you cluster, or the kind of clusters which are formed will depend on the distance measure you use. That is why the previous lecture of distance functions are necessary here. Okay, so let us start that again. This is data points. There are data points t, x1, x2, so on up to xn, and all of them belong to some rd. Okay, these are all vectors. And now we have to form them into k clusters. K is given. So how will you define what is a cluster? What is the cluster? We have not said what is a cluster. So how can you say what is a cluster? So you can think of a cluster as a set of points such that the intra-member distances within that set is less in one cluster as opposed to the distances from the points in the cluster to the points outside the cluster. Okay, so this distance, the set of points which form the cluster, the distances between them are less than the distances to points outside the cluster. So that is, you can roughly say what is a cluster. So to define what is a cluster, we define what is known as a mu k, which we call as a prototype for cluster K. So prototype is a cluster is such, let's say, some representative which represents all the data in the cluster. So that representative could be, for example, some data maybe in the center of the cluster. Okay, so that could be something which represents one cluster. So we will see what that prototype is. So now to formalize the problem, we will use a binary indicator random variable, let's say, which we call RNK, which takes the values 0 or 1, where k goes from 1 to k and n goes from 1 to n. N is the total number of points which are given to us. K is the total number of clusters that is also given to us. And the value of this is if xn is assigned to cluster K, Rnk equal to 1. Else Rnj equal to 0 when j is not equal to k. Okay, so this is how the binary variable Rnk is defined. So Rnk means if R, let's say if you are considering the variable R23. So R23 is either 1 or it is 0. So if it is 1, it means that the data point 2 is assigned to cluster 3. Okay, so that is the meaning of Rnk. So now we can formally write the problem. We can write an objective function. We have to determine, let's say, some j such that n equal to 1 to n, k equals 1 to k, Rnk, we are using xn minus mu k the whole square. So basically what we are writing, what we have written here is, we have computed the distance from every data point xn, so from every data point to to some cluster centroid mu k, to some prototype of the cluster mu k. We have found out the Euclidean distance. Here it is the L, here we have used the L2 norm. Basically, this is the square of the norm between xn and mu k. And we are weighting it by the binary variable. So that means if this xn is assigned to mu k, then this variable takes the value 1. Otherwise, it takes the value 0. So now our objective is to find out the Rnk and mu k such that j is minimum. So the objective is now to, because we don't know what is mu k. Initially in the beginning, we don't know what is mu k. We don't know what is Rnk because this is actually the assignment. We only have xn. So now our objective is to minimize this. So this kind of optimization is usually done in an iterative manner in a two-step procedure. So first we will choose some initial values for the mu k. Choose some initial values for mu k. I will just actually these are all vectors. Choose initial value for mu k to minimize j with respect to Rnk, keeping mu k fixed. So you fix the mu k and you find out what are the Rnk's which minimize j. Then you repeat. Then in the next step, minimize j with respect to mu k, keeping Rnk fixed. And this step you repeat. You keep repeating this until j reaches some minimum value, which value below some minimum which you are willing to tolerate. So this is basically a iterative two-step procedure. In the first step, you keep one set of unknowns fixed and find out the minimum for the other set of unknowns. So you keep one fixed. So there are two unknowns here, which is the mu k is unknown and Rnk is also unknown. Only xn is known here. So in the first step, you fix the value of mu k and find out what is the Rnk which minimizes j. In the next step, once you determine those minimum values for Rnk, you keep that fixed and then minimize again the j with respect to mu k. So, and then you keep repeating this. Okay, so this is how the optimization proceeds. And you can actually find out the values for Rnk. So for the, let's say, to do this step, for example, this step is done by you to find what is the minimum value for Rnk. That minimum value for Rnk is going to be, Rnk is either 1 or 0. So this will be 1 if k equals argmin xn minus mu j the whole square argmin over j. So basically, how do you find out the how do you for one particular data point, let's say, how do you decide which cluster to assign it to? You basically find out the distance from that point to all the cluster prototypes. Whatever is the minimum, you assign it to that cluster. So that is why RNK is 1 for that particular k. The k which minimizes this distance. And the second step, you can find out by differentiating with respect to mu k and equal to 0. And that will give you 2 sigma r n k xn minus mu k is equal to 0. And this will give you mu k is equal to sigma over n r n k xn by sigma over n r n k. This you can get it by just simply expanding this. Expand this summation here, and then you can differentiate with respect to mu k, and you'll get this answer. Open out the summation and you'll get this answer. So mu k is given by this, and basically what does this mean? This is, so what is this total number of RNKs? Total number of RNKs over all n. This is for a particular k. Okay, this is for a particular k. The summation is over n. So basically this is going to give you the number of points which are assigned to cluster k. And this is going to give you, in this case, RNK is always going to be 1, because this it will sum only the points which are assigned to the kth cluster. So essentially this will be the sum of all the xn's which is assigned to cluster k, and this is the total number of points which are assigned to cluster k, and that means basically this is the mean. Mean of the data points assigned to cluster k. So that is why this algorithm is called k-means clustering. This is the k-means clustering algorithm. And this is the k-means clustering. Whatever we just defined here was the k-means clustering. Okay. Yeah, so these topics I've covered from Bishop. You can have a look at it. And yes, since yeah, I don't want to cover too much also in the online mode, so we'll see. Okay, any questions at this point? I will revise this notes and upload it on Moodle. Okay, if there are no questions, then we will meet. I don't know when, but I'll let you know about the next class. Fine. So I'm stopping presenting. Yeah, you can leave.